So I think we can start. So our first speaker today, Pasquale Serpico. Please.
Okay, so thank you everybody. Thanks for being here and for to the organizer for the invitation, not only to be here but also to present some results. First of all, I think I must apologize. I owe you an apology in the sense that this is my plan B. I was not supposed to talk about this. I planned to talk about another work, which is in progress, and I was too optimistic. I would have thought that I could present some results by now. So the choice of the topic I'm going to introduce today is due to some other considerations. One of these being that it's suitable for a half-an-hour presentation at the Blackboard. I was invited in particular by Guillermo to prefer this option. So if you don't like the result, blame me. That's the question. Okay. Concerning the topic, first of all, let me give you a preprint number. This is 2208 06 0, where you can find many more details, boring ones concerning the topic. And the topic is essentially a apparently trivial one. Namely, I'm going to be concerned with the fate of an ultra-energy photon, and I will define what I mean by ultra-energy photon, in the early universe, where early universe here is according to the astrophysicist definition, not the particle cosmologist, namely redshift around 10, say. So at the epoch of the first star forming, well before what you have been observing right now. So it's the James Webb Space Telescope realm, if you wish. So again, ultra-energy photons at redshift, let's say, much larger than 1. But much larger is again not cosmological in the early universe sense. By ultra energy here, I mean, loosely speaking, something like larger than 10 to the 17 electron volts, and will be maybe a bit more specific in the following. But this is the range of energies of interest for detectors like maybe the Pierre Auger Observatory, at the edge of maybe what is of interest for IceCube or future detectors like GRAND or in the neutrino channel. And why is this an interesting topic at all? Because what we realized, this work has been done in collaboration with Arman Ismaili and students from Rio de Janeiro in Brazil, over a visiting professorship, basically, during summer. This has to do with the fact that this problem has apparently been overlooked in the literature. So there is a lot of studies in high-energy astroparticle physics about the fate of energetic particles, protons, photons, neutrinos, whatnot, in the low redshift universe. But what happens to them in the high redshift universe is either neglected, or when it has been treated erroneously. So there are wrong conclusions in the literature, and even the literature reduces to maybe 3 papers over 20 years or something like that. Okay. So in order to understand this thing that was quite surprising to us, but we came to this conclusion. I have to explain to you what is the standard law. Okay, so what do we expect the fate of an energetic photon to be if you inject it in any? Here I won't be concerned about sources of these photons. They can be astrophysical sources, they can be new physics sources. It doesn't matter. Okay, what is the fate of such a photon? 10 to 18, 10 to 19, 10 to 20 electron volts. These are the typical scale of the highest energy cosmic rays that we have measured. That's what I have in mind. If you inject them in the low redshift universe, okay? What you might be familiar with is the fact that the universe is filled by many types of backgrounds. And in fact, at energies well above the well above the PeV, but already at supra TeV energies, the universe is essentially opaque to photons. So what happens is that these photons, these energetic photons, will hit some background photon and pair produce and go into E plus to minus. And the background you have to be concerned about are, of course, the CMB, the EPL. This one, sorry about acronyms, but this is standard in the literature. So this is an infrared to ultraviolet background associated to stars. And URB, the universal radio background, which is associated to a non-thermal type of emission. Non-thermal type of emission of different type of processes that I won't be concerned about. And then what happens to these pairs is one of the two following things. Either the electron positron will inverse Compton scatter on the backgrounds, and then you will have an upscattered photon. If this happens in the Thomson regime, which is when essentially the energy of the electron times the energy of the background photon is much smaller than n electron squared, then what happens is that there is a low inelasticity for this process, so the electron will retain much of its energy. The energy of the photon will be upscattered. This photon will be upscattered to energetic values, but still it's much smaller than the energy of the outgoing electron. So this is behaving like a continuous energy loss process, and I won't be concerned about that. In the Klein-Shannon limit, instead, which is the opposite one, what happens is that you basically switch the role of the electron and the photon. So the inelasticity is high. And at leading order, you can just assume that the energetic electron is replaced by an energetic photon, like billiard balls. And then the energetic photon will start again a cascade if it's above threshold. Okay, the threshold here is m e squared over the typical energy of your background. This is trivial 3D processes. There is another possibility this electron cannot go through, which is the fact that it acts on basically synchrotron losses on some magnetic field. Okay. This possibility is borderline in the sense that it's barely relevant if the extragalactic magnetic fields are at the upper limit of what is allowed, the level of nano-Gauss over cosmological distances. Otherwise, it's negligible. Okay. At the end of the day, the result of this key interaction is to develop a shower, of course, because now you inject. It doesn't really matter if you inject a photon or an electron or a positron, in fact. It just changes the starting point. But you start pair producing, then the electron gets converted back into a photon. The photon pair produces again. You have a multiplicative shower where the number of particles increases, the energy decreases until this goes below the threshold. Okay? And
sorry,
yes.
Sorry. The energy of the gamma prime versus the gamma background, how much?
This one?
Yes.
So there are two limits. The energy of the gamma in this limit, in the Thomson limit, the energy of the gamma prime is roughly given by the background energy times gamma squared. So the energy of the electron over the mass of the electron square. Okay. In the opposite limit, the energy of the gamma prime is essentially the energy of the electron. Maybe a factor 0.9, 0.95, something like that. Okay, depending on exactly your kinematics.
So what is the nuclear path?
Yes, that's the other interesting information. So the typical mean free path. This is not the bottleneck. This is very fast. So this is what determines actually the mean free path for a cycle. And let me use colors this time. So for the interaction, if this is the energy of your photon and this is the mean free path, for the interaction on the CMB, this is not right. I'm really bad at drawing, but clearly there is a threshold effect. So it should be something like more like very sharp here. This is more correct. This minimum corresponds to roughly PV, and the mean free path is of the order of 10 kiloparsec. So basically, this is telling you that the PV energy, we are blind to anything outside our galaxy, essentially. We are photons. This is for CMB. Then the EPL will act here, and the radio background will be important somehow here at 10 to the 18 electron volt or so. And roughly, well, these are perhaps comparable. This depends on the models of EPL and the radio background. But these might be, just to give you an idea, maybe 10 megaparsec, something like that, to give you a scale. So the extragalactic sky and these energies where this starts to become below the Hubble horizon is of the order of, I don't know, several TeV, maybe, let's say 110 TeV. So essentially, the reason why you haven't heard so much talking about gamma ray telescope at very high energies is because the extragalactic sky is opaque. And some telescopes that do measurements at high energies, even in the gamma band, like Tibet AS, LASO, you may have heard about this, are essentially galactic astrophysical instruments, not extragalactic ones. Now, what happens to this energy?
At PV is when I produce the plus minus threshold.
Yeah, this comes from the fact, yes, there is another information, you're right, that I didn't tell you, is that the cross section versus S for your pair production peaks essentially slightly above threshold. This is the threshold that you see there, and this is a few times that value with a long tail where it decreases. Now, what happens to this energy that you inject is that modulo these magnetic synchrotron channels, which drains energy to low energy photons. This can be from radio to X-rays, depending on the energy scale and the value of the magnetic fields. All of this energy will go in gamma rays below this threshold. And this threshold, the lowest threshold, is going to be this one, this EPL. This radiation is the radiation in the infrared, optical, and ultraviolet due to stars being produced all over the history of the universe. That's what we are talking about. It is going to end up in the sub-TeV regime, but in an isotropized way. So essentially, we have only a calorimetric type of information about the gamma ray sky above PV energies. And this is what has been measured in the isotropic or quasi-isotropic gamma ray background by instruments like Fermi-LAT. Okay? This is the standard picture at low redshift. What happens at high redshift is that essentially these will disappear eventually because the star formation rate peaks at redshift roughly 2 or so. And anyway, the CMB will grow in number as 1 plus z cubed and in energy as 1 plus z to the 4th. This one will disappear as well. This is due to loss of non-thermal astrophysical activity, but it's typically a decreasing function of redshift above, again, the scale of redshift 2 or so. So the relative weight of this heavily favors CMB with respect to the others, and above redshift 10, basically there is none of these, and only CMB is left. Okay? What happens in this situation? Well, it's quite different from what I just described you. And
the source is probably just beyond this kind of volume.
well, not really. There are at least a couple of sources that are possible. One is a stellar phenomena associated to the first stars. So the first supernovae, the first gamma ray bursts, things like that. The other putative source, but astrophysically they must be there, are related to the growth of the supermassive black holes. You might be familiar with the fact that we have inferred the presence of objects which are as heavy as 1 billion solar masses at redshift above 7. So they must come from somewhere, maybe from stellar objects, maybe from physics, whatever. There are accretion phenomena clearly associated with them. So there should be some astrophysical acceleration. So I am rather agnostic of what these spectra of energetic particles should be, but there is a few likely sources of very energetic objects at high redshift. It's just that the background in which they evolved is very different. Okay, so let me just erase this and tell you.
Can I ask
you, sure.
What are the highest energy photons which are seen?
There are no confirmed high energy photon events. In the high energy being here Auger scale. For the detected one must be hundreds of TeV, something like a few hundreds of TeV. I don't know the exact number, but now there is a claim that even LASO is starting seeing in the tens of TeV, which is quite surprising. You might have heard about that in relation with a nearby gamma ray burst, but I won't enter into that. So it's very hard to infer, to tag a photon as a photon in the ultra energy cosmic ray regime because it's highly indirect. You must study the shower characteristics. So the richness. So the muon poor showers, for instance, are candidate photon-induced showers in Auger. Say so they have been searching for them. They haven't found any. There is a guaranteed minimum number of photons associated with cosmogenic. It's the counterpart of cosmogenic neutrinos. Essentially, you will have a few protons interacting with the CMB in the nearest tens of megaparsec. And from pi0 production, they should have some photons. But this is the lowest limit. We don't know if there's more. And we didn't expect actually Auger to be measuring photons, but for very optimistic models, let's say. So what changes the picture in the high redshift universe is that only the CMB is left. And then what happens is that above an energy, which is, let's go MPP, which is roughly 2 times 10 to 19 electron volt over 1 plus Z, you have this channel which is open, gamma gamma into mu plus mu minus. Now the cross section for this is much lower, of course. It's suppressed by m squared compared to the case of the electron positive. However, what happens is that since you don't have any other target onto which to pair produce, the E plus E minus pair production is again characterized by the very high inelasticity. So the mean free path for E plus E minus production is irrelevant in a certain sense. What you care about is the energy loss length, because one of the two leptons will carry the largest fraction of the impinging photon energy. So you need maybe tens or hundreds of interaction before you have an E-fold reduction in the energy of your photon. Okay, that's the key. When there is extra background, you can produce near threshold, so to speak, at the peak, and then the kinematics is such that you split your energy, you degrade your energy. Since this the E plus E minus is characterized, if it's only on CMB, by a very high inelasticity, basically the cycle will be just So in each of these steps, one of the particles will be very energetic and one of the particles will be very low energetic. And you have to do many, many steps before the photon has degraded its energy with respect to the initial energy, right? So even if the cross section for this is suppressed by a factor maybe 5, 10 with respect to this one, it's very relevant for energy losses. Okay. There is another thing that of course, you should worry about the additional 3D processes that are allowed. Another important process that is important is gamma is the double pair production. And the kinematics here is different. It's rather flat with energy, and it's slightly bigger, the cross-section than this one, comparable roughly at the peak. So I think maybe this is a good moment to show you some picture from the preprint, to avoid drawing 3-4 figures by hand. Yes. Okay, let me just tell you in meanwhile what happens. So I draw maybe here some figure by hand. So despite being Italian, I'm not a good drawer. So what I wanted to draw here is something like the characteristic length, to which the typical distance over which it works.
Work slowly, but
Okay. You go to page 4, figure 1. If you manage.
jump with the menu on the top instead of scrolling.
Yeah, okay. So this is the first figure I wanted to show you. So what you see here is in blue, the energy loss length of E plus E minus. In green is the muon per production energy loss length, or interaction length, which is the same. And in black is the double pair production, the double pair that I just erased. And these are compared with the Hubble length at 2 redshifts. These are appropriately rescaled so that in these variables, the particle physics processes are universal. But of course, in this variable, E times 1 plus Z and characteristic length times 1 plus Z cube, the Hubble length will have to be rescaled as a function of redshift. So what this shows you is that you have a very, very, this is the 10 kiloparsec scale I was mentioning before, a redshift 0 for the minimum mean free path for electron positrons production. And this is at the scale of maybe 100 megaparsec at redshift 0 for the muon pair production. All of these scales are well below the Hubble radius, which means that essentially they happen, these processes happen instantaneously compared to the cosmological evolution, which helps a lot in the quantitative calculation. Why you need, actually, in order to understand what happens to the spectra, to the energy flow, to the spectrum of these particles, unfortunately, the fact that you have multiple type of processes requires some Monte Carlo. That is what we did. So we followed something like 10,000 photons, and so how they degrade their energy, what happens to their spectrum and to the associated neutrino spectrum that comes from the muon decay. Okay, and maybe if we can scroll to the figure 2, which is page 5, the following one, this one. Okay. Yes. So this is the results of these calculations. On the top, so the 3 columns represent 3 redshifts: redshift 5, redshift 10, redshift 15. Why this redshift? The point is that it's model dependent at which redshift you can neglect all these other backgrounds. If you trust baseline models above redshift 3 or so, they should be relevant. to be on the safe side, we assume that these considerations are only relevant above redshift 5. For the magnetic field, the discussion is a little bit different. If you are curious, I can come back to this. But this is essentially the redshift range where we believe our considerations are physical. So at close to the threshold, of course, only a small fraction will pair produce muons, and more than 80% won't. If you go up in redshift, this fraction of non-muon pair producing photons will decrease. It will decrease even more wildly if you go to higher energies, so that at 10 to the 21 electron volt, which is roughly the scale of the highest energy particles we have ever measured, this fraction is 0. So at either large redshifts or large energies, all photons will have produced at least one muon in this cascade, in this anomalous high redshift cascade. Okay. You also see that this distribution is very broad. In fact, this is the distribution of the fraction into neutrinos, which is a proxy for the fraction of objects that go into muon channel. And it's very, very broad. So these guys, there are a few cases where the neutrinos will carry maybe 80% of the energy of the photon. And typically, these are in the, let's say, 0.2 to 0.8, so 20% to 80% range. This is maybe more explicit. This is the fraction going into neutrinos as a function of redshift for 3 different energies of the injected photons. And the bar represents the 1 sigma around the mean. You see that close to threshold, this fraction is low. It grows and becomes almost constant eventually, around 25%. This number you can roughly guess analytically. There is a discussion in the paper to justify where this number comes from. The spread shrinks a little bit with energy. And this makes sense. It becomes more deterministic in the sense that you have now a shower constituted by a large number of particles, so that the distribution is more sort of universal and narrower. And another thing which is interesting, maybe if you can scroll just down half the page for this figure here, is that the number of muon pair production events that you can produce is non-negligible if you go to high energy. So at the beginning is either 0 or 1. But in fact, because of the double pair production mechanism, what happens is that you multiply the photons for each photon of very high energy. You multiply through multiple pair production. You multiply the photon followed by inverse content. You multiply the photons that can pair produce. So eventually, the double pair production, what it does is essentially to take a photon of 10 to the 21 electron volt, say, reduce it to 10 photons or 50 photons of 2 times 10 to the 19, and out of these 50 photons, maybe 20 or so will undergo muon pair production. That's the basic description of this phenomenon. And what are the implications of all that? Maybe if you can go to the last. Yes.
Sorry, can you explain a little bit why does it become universal, the distribution of your neutrinos as you go above a certain threshold? Shouldn't you be producing more and more the higher the energy?
It's just that each photon, because of this process, each photon, in fact, will be associated to a number of daughter photon showers. Yeah. So it's not anymore a type of one or off. In this case, in near threshold, either your photon will interact with muon pair production, or it will interact via some electron-producing phenomenon, and that's it. If you are a very energetic photon, what will dominate is, in fact, the double pair production process. So you produce 4 electrons. Yeah. And the kinematic is such that 2 of them will carry most of the energy, yeah, and almost equally split. Okay? This is just from the QED calculation. And then, so this photon will in fact multiply, will multiply till you get very close the peak of the muon pair production cross-section. And at that point, these 20 photons, 10 photons, whatever, will muon produce with a fixed probability. So in practice, since you are in a large n sampling limit, you get always the same result, basically. You are less Poissonian dominated. That's it. So
it's not realistic is to think of these super high energy photons you are assuming, like 10 to 21.
Well, what matters is actually the product of the energy and the redshift. So what really is the key variable is E times 1 plus Z. So essentially you get a similar results as an energy of 10 to the 20 electron volt at redshift 10, as you would get a 10 to the 19 electron volt at redshift 0, although at redshift 0 you cannot extrapolate because of this. So it's less extreme than it looks. So just to give you an idea, if you just assume that ultra energy cosmic rays should be able to produce to be produced in a similar way as they do at low redshift, you would expect photons up to 10 to 19 electron volt or so. So if the high redshift universe is essentially like the low redshift universe in terms of high energy astrophysics, these photons should exist.
You are going to compare with the redshift. That's what you are saying.
Yeah, you are going to redshift them, whatever you produce, but this is a different story. What matters is the redshift at the production time for this. So if you go to the figure, yes.
So why are we not including the hadrons?
Which hadrons?
Ions?
Sure. You could. It's just that the charged one, they are suppressed. I mean, the cross section for photon production of ions is suppressed, but around let me see, the F2 270 resonance. So essentially, it's just it wouldn't change much the result. The pion would still behave roughly like the muon. You would get a slight increase in the conversion fraction into pions. For the heavier hadrons, this is even more suppressed. So counts and all that is less relevant. But there are other processes that we neglected. I mean, this is the first study that tries to get the picture right. You can imagine including them, triplet production and the like. And the reason why we neglected that, so it's like E gamma E. The reason why you neglect this is not because the cross section is negligible, it's because the inelasticity is very, very low. So the pair here carries maybe 10 to minus 3 of the initial energy. So you need 1,000 of these processes to happen before they do something relevant. But of course, if you are interested to a percent level calculation in terms of precision, you should include these things.
Right. At least the pion should behave. It doesn't exactly like the muon. That's give you.
Yeah, but the cross section is lower. It's an order of magnitude or more lower.
But it's only between 100 and 140. There's nothing.
It's not about. It's not about. I think it has to do with the hadronic content of the photon. There is a penalty that you pay.
But you just look at photon collision, no?
But why there is the
just the photon?
Why there is electron?
Yeah. What is
Here?
Yeah.
Because in the phase where you convert your photon, you pair produce. Yeah. So you decay from your muon into electron, then you have some energetic electrons.
No, but back again, the initial thing is just photon CMB, right? That's what you have, no? Or it starts with a photon hitting a CMB photon. So just a gamma-gamma collider. So you have pions and muon the same way.
It's not the same cross section.
Well, at threshold, I agree with you.
Yes,
there is no difference. There is a factor of 4.
Four.
Yeah, but the threshold, once you go to 10 to 21, who cares about the threshold? You are above the threshold. So then,
if you go above the threshold of mass,
no, that's not how it works. Maybe if we, again, this is the crucial thing. The process is such that the double pair production is what matters. Okay, so what you do is, because the double pair production, gamma gamma into E plus, E minus, E plus, E minus, is the dominant process at high energy. It becomes comparable to the muon pair production at the muon pair production threshold, or near, just after it, let's say, at the peak. So at the end of the day, what happens is that at that point, you are a bit too low for the pions, so you should not compare. This is a slide, sorry, I don't have the plot, but essentially, again, the plot would be, this is the muon pair production, then you have the length as a function of energy, and this is the essentially it's flat, the double the double pair production. The pion would be something like that in this plot. What this guy does is to bring a lot of, you take a photon, split into as many photons as the ratio of this energy to this energy, and at this point, you have 50% chance for each photon to initiate a muon pair production. Now, you have to compare not this with this, but this with this cross-section. And there is a suppression which is significant.
Because you fix the energy, the incoming energy, otherwise I don't understand.
Even a difference between 100 MeV and 135 MeV is such that you pay a penalty because of this, because this is a very steep curve. I'm not drawing it right.
It's a fixed energy, I agree with you, of course.
Yes.
But if you have much more energy than...
No, because the double pre-production is what matters. So the double pre-production is such that it drives all of your energy near this point. At this energy, you do not produce muons.
I'm sorry,
because
at that energy, you actually produce quarks, not pions.
Of course.
And you have probably produce more.
It's just a shower with gamma-gamma collider, and we know how the shower, once you're approaching above half a GeV, gamma-gamma to half is...
I cannot claim, I mean, this problem with pions was studied by Lee in 1996, so we get the reference there, and this conclusion comes from Lee in 1996. But I cannot...
At the fixed energy or the energy which is
which is fixed. The energy of the injected photon is fixed, but it doesn't matter for the muon production mechanism, because what it matters only in determining how many photons are at the peak of the muon pair production. At the leading order, that's what happens. You will never produce muons at an energy of 10 to 21 electron volt for the impinging photons. The photon of 10 to 21 electron volt will transform into 10 photons of 10 to 20, and these 10 photons will have 50% chance of inducing a muon. That's the way you should look at it. And at this energy, which is close to the threshold for the muon, you have a suppression for the pion, and this is what determines the fact that this is a subleading process. That said, if we were to basically treat 1 in 4, 1 in whatever as a pion, you wouldn't change very much, because you are still dominated by the charged pion production, and then in terms of neutrino flux, you get something very, very similar.
Yeah, that's
okay. So neglecting this just makes slightly more conservative our conclusions. For the heavier hadrons, it might change, but for the heavier hadrons, you have a much more significant suppression. So the only way this conclusion can be altered is if you can find new hadronic processes that win with respect to the double pair production, not with the muon pair production. It's the double pair production that you should overcome. Anyway, just to conclude, these are the spectra that you would expect. So just look at the blue curves. These are the typical spectra of the neutrinos that result from this process, here injecting a 10 to 20 electron volt photon, for instance. These multiple bumps are associated with the fact that you get the neutrinos for 1 cycle, 2 cycles, 3 cycles, in the sense that sometimes you can get the electron resulting from the decay of the muon to initiate, through conversion into photons, a new muon pair production event. And this gives you this multiple generation thing. Till now, I didn't say anything about the sources. If you trust the standard law that these high energy photons are likely to come from pi0 decay dominantly, then you should expect that the photons are accompanied by neutrinos, primary neutrinos, coming from pi plus and pi minus decay at twice the energy. Okay, so this is then the total neutrino spectrum that you would expect in these scenarios from P gamma or PP production, and you see that they are quite separated in energy space. So what the signature in conventional astrophysical scenarios of this mechanism would be is to see a shoulder at low energy where this takes over, and I didn't overlay here the sensitivity of typical ultra energy neutrino telescopes, but it peaks rather here than here, actually. Of course, we don't know if the high redshift objects dominate the total budget, if everything is trivial, we should expect that they don't because of the redshifting event. But if you have a lot more energetics in the high redshift universe than you have in the low redshift universe, we cannot exclude that, then you might be able to see this at future telescope like GRAND. Okay, and another thing that this does is to change the ratio of energy between maybe where is the I can show you the equation or just sorry, just here. Nothing up. Yeah, it's very slow. Just lower the page to this equation now. It's the same page, just the. So the typical argument people have used also to gauge the size of, say, neutrinos telescope you want to build was to use essentially this relation that comes from pion universality. So this links the energies at production, the energy spectrum in photons, the pions, to the energy spectrum in neutrinos. Okay, and it only depends on this factor K, which is either 1 or 1/2, depending if it's the PP or P gamma process that dominates. Now, you can integrate these two in terms of energy, as long as it's calorimetric, the cascade I was describing before, you get a universal ratio between the energy, the calorimetric content of the energy in the sub-PV regime linked to the energy of your neutrino. And this relation is altered, and it's altered in favor of neutrinos. So you get a 40% change, which is not negligible. So somehow the high energy universe, there are two lessons. To take away lesson is, one, you can still see what happens to the injection of ultra energy stuff in the Earth universe through this neutrino memory. Okay, although the photons are degraded, you can still see the neutrinos in principle. And the second is that the high energy universe is more neutrino rich and comparatively photon poor than the low energy universe. So this is another thing that people just overlooked for some reason. And these are the two takeaway messages of this. So one optimistic, one pessimistic, if you wish. I don't know if you have questions, but otherwise I stop here.
Thank you, Pasquale. Perfect timing. But so yeah, are there any questions? Yeah, time.
So you expect to measure this shoulder shape when you have hope because
it's the other way around. I mean, if you measure some feature like that, this might be an explanation for its origin. Of course, we don't know what the sources at high redshift are. Sure. And unfortunately, this is something people don't realize. Unfortunately, we will never know. So neutrinos are the only way to assess this, because photons are absorbed. Ultra energy cosmic rays are are absorbed through GZK-like features that now happens at lower energies, and they will be reshifted as well. So they are probably subleading to whatever component we see in the, say, Auger spectrum right now. Gravitational waves, sure, Einstein telescope should be able to see coalescence of very high redshift black holes, but it's unclear how much these objects are related to non-thermal emission, right? So it's very hard to know, once you detect this background, what produces it. And one diagnostic might be
you have a funny signature, which is also at the peak of that spectrum. You have this step.
Yeah, but this is the pion. This is artificial in the sense that it's the fact that from pion decay, you have both the direct neutrino from the pion decay into muon, and then you have the continuous spectrum from muon decay into pion. It's not artificial in the sense that if you had a monochromatic beam, you would see it. But as soon as you have a dispersion of energy, it's moving down.
Also connected, is there any also portals to new physics that imagine that you
in principle, what could there are many exotic. I am not very familiar to BSM type of models that produce relic that somehow have disappeared at this epoch, but it's a possibility, right? So something that decays at redshift or whatever, 10, 20 or so, cannot be the dark matter, but you could have relics from the early universe that do that.
For example, when action mini clusters may decay to. I mean, there are these models I heard about.
Yeah, I mean, for the time scales, I'm not sure if they work, but honestly, in this paper, we didn't want to speculate. There are a few references that we gave, but in general, you must make sure that you do not disrupt other things like the CMB observables and whatnot. But it's fair to say that people have not looked that much into these possibilities. This might be of interest also for other type of cosmology, like 21 centimeter cosmology. We really don't know what are the processes going on at redshift 10, both standard and non-standard. So maybe there is room for surprises. It's just that the message here, don't give for granted that the naive astrophysical expectation that you apply to low redshift universe hold here, because of the fact that only CMB field universe has a completely different kinematics and relative weights of the microphysics processes. And here there is no, this is just 3D in a certain sense. There is no BSM physics.
Related question. Within standard model, can you think of any channel or process that you have neglected just because it was difficult to think about it now? So for example, the hadronic, you seem to have it under control, no? Well, based on the cross-section argument.
We basically trusted some older paper that consider this a sublink. It's not irrelevant. It's just sublink. Okay, so we can correct the 10% level these things. For the others, I don't see. Okay, one thing that we simplified a bit the kinematics of the double pair production, because this is imagine a Monte Carlo where you have to follow the Padre differential distribution. It's very slow, but there were other papers that studied some of the approximation that we did, and they found it to be correct at few percent level. Okay, this process. Why do we stop at 10 to 21 electron volt? First, because we haven't seen any object, any high energy particle above this level, but also because then you should care about this process, which starts having an inelasticity which is non-negligible. So the claim that this can be neglected breaks down. So all these are, I would say, few percent type of corrections. The major one that was neglected in the past was this rule of the double pair production. And surprisingly, there was another study, I think by a Chinese group, that considered these processes, but in the low energy universe with all these other backgrounds involved, and they found a percent level correction to the standard pitch, of course, because you are not in the right setting for them to be important. So.
Okay, very good. So I think we can move on. Let's thank Pasquale again.